We're going to go ahead and take a look at complex numbers. For the most part, we're going to spend most of this lesson learning about how to simplify square roots that have a negative on the inside. Earlier in this chapter, we said we could not take the square root of a negative. We could take a cube root of a negative, but couldn't do a square root of a negative. So we're going to explore a new concept called complex numbers. Now, by definition, the square root of -1 is referred to as I. I is called the imaginary unit. And a complex number is a real number, a number that doesn't have i's, like 5, plus something that does have I, like the 2i here. So any complex number is often written in the form of a number that has no i's plus a number that does have i's, as in a real part plus an imaginary part. And imaginary numbers do have applications a lot in electrical engineering. They just kind of have a bad name. So for example, the square root of -4 is really a 4 times a -1. Well, you guys know the square root of 4. Oh, that's 4 should not be there. Sorry. That 4 is a 2. Okay, so then we'd have square root of -1 times a 2, and by definition, the square root of -1 is I. Another thing we need to talk about is conjugates. A conjugate is when you just switch the sign in between, not switch both signs. Don't switch the sign in front and in the middle, just the one in between. Switch it from a plus to a minus, or from a minus switch it to a plus. So these two are conjugates, these two are conjugates. So if you switch the sign in between and you're only switching the sign in between, these two would be conjugates. Conjugates are going to come into play later when we have i's in the denominator, because we used conjugates earlier when we had two terms in the denominator. One of them had a root and one of them didn't. So we're going to simplify these roots. So I'm going to rewrite this. We're going to be simplifying these roots very similar to what we did before, except if we have a negative inside of a square root, I'm going to put it as a -1 times the rest of it. Now, we already have dealt with the square root of all this part here, just not with the negative. Well, the 32y cubed inside of our square root will simplify like we would normally. And our 32 is a 2 to the 5th, which we would write out as a 2 squared, and another 2. Then our y cubed would be a y squared and another y. Now we can start pulling stuff out. Now remember, the square root of -1 is an I. Square root of this 2 squared is a 2. Square root of this 2 squared is a 2. Square root of this green y squared is that. We can't do anything with this normal 2 and this normal y. They stay inside of our root. So we end up getting a 4i times y with this square root of 2y left inside here. So pretty much, if you have a negative inside of a square root, you're going to have an I in your answer. Now, it's only if you have a negative inside of a square root. It does not apply to other roots. It's only a square root. So this one here, we're going to write it as a -1 times 50 x to the 5th. Then our square root of our 50 x to the 5th, we'd work out like we did in earlier sections. So square root of this green -1, you know, is an I by definition. Square root of that 25. Square root of our 2x squareds. Can't do anything with the 2 or the x. So we simplify what's in front to 5x squared I, still with our 2x inside. So the main difference we're doing today is just dealing with the negative inside of a square root. Now, what happens when you're multiplying two roots and they both have negatives in? Well, first of all, you have to simplify. So you'd simplify your negative square root of 12, square root of your -1, square root of your 4, still with the root 3 hanging out. And we'd simplify our square root of -2, which you know is a -1 times 2, and pull out that square root of -1 as an I, still with the root 2. Now, once you simplify the roots first, then you can go ahead and multiply them. And remember, in multiplying roots, you multiply what's in front. 2i times I, and remember I times I would be I squared, and then multiply what's inside. Now, as a side note, I by definition is the square root of -1. So if you square both sides, you get I squared on the right. You square the left side, all it's going to do is undo your square root. So your squaring undoes your root, leaving you only with -1. So by definition, I is the square root of -1. And doing a little bit of algebra, we end up really realizing that I squared is -1. So this I squared here is a -1. And then in front, we really just get -2. So we just talked about I squared a little bit. So what about I cubed? Well, remember that an I cubed would be like an I squared times an I, which would be I squared's -1 times an I. In other words, it's just -I. Or like an I to the fourth would be an I squared times an I squared, which would be a -1 times a -1. Well, that's just +1. And so we have these here. So then what do you get when you're dealing with something like I to the fifth? Well, that would be an I to the fourth times another I. So that means this is just an I here, because remember, I to the fourth, what we just figured out over here is 1. So then we look at this one here. This is just an I to the fourth times an I squared. Well, once again, that's a 1. This is a -1. So we get just -1. And we can continue this. This would be an I cubed times an I to the fourth, which would be I cubed is -I to the fourth is 1, and so this also ends up just being -I. I to the eighth, it would be an I to the fourth times an I to the fourth, or 1 times 1, so it's 1. So I to the ninth would be I to the fourth times I to the fourth times an I, so it would be 1 times 1 times I, or just I. And that pattern continues. So in other words, if you look at your exponents over here in the far right, 4, 8, 12, if your exponent's a multiple of 4, then your answer is always just 1. If your exponent over here, like I to the first, I to the fifth, I to the ninth, 1, 5, and 9 are always 1 more than a multiple of 4, and that's what this is saying. If your exponent's 1 more than a multiple of 4, then it's just I. Here, these are all 2 more than a multiple of 4. If your exponent's 2 more than a multiple of 4 on your I, you get -1. If it's 3 more than a multiple of 4, then you get -I. So when we're working something like I to the 37th out, you got to ask yourself, is 37 a multiple of 4? And you're like, no, but 36 is, and 37 is 1 more than that. 1 more than a multiple of 4 is just a normal I. Then you look at this one. You ask yourself, is 16 a multiple of 4? Yes! And anything that's a multiple of 4 is a 1. Then you look at 43. Is that a multiple of 4? No, because it's odd. But 40 is a multiple of 4. And so 43 is 3 more than a multiple of 4. Anything that's 3 more than a multiple of 4 is -I. 33 here is not a multiple of 4, but 32 is, so 33 is 1 more than a multiple of 4, so that means that's I. So if you're dealing with powers of I, it's only going to be one of these 4 options, and it all depends upon whether it's a multiple of 4, 1 more than a multiple of 4, 2 more than a multiple of 4, or 3 more than a multiple of 4. Here, we're just multiplying. We can multiply in any order, so we can multiply the normal numbers and then take I times I. So we get a -6 in front. I times I is I squared. Remember, I squared is -1, so it's a -6 times a -1, or a +6. Here we can multiply. We have 4 things multiplied together. You multiply in any order. Multiply the numbers together. Multiply your i's together. Remember, I squared is -1, and we get a -15. And here, this is 1 more than a multiple of 4, so it's just I. Now, This problem here, all we're doing is we're subtracting two complex numbers. Well, parentheses aren't doing anything here. Since it's a subtraction sign, we have to distribute through that subtraction sign, and so we end up getting this. And now it's just a matter of combining like terms. Our normal 4 minus 3, negative 6i plus 7i is positive 1i. Over here, we're adding in between our complex numbers. Well, if you add in between complex numbers, if you add anything, you can add in any order you want. The parentheses aren't doing anything, so you can take your normal 3 plus your normal negative 2, and you get 1. And then you can take your 2i plus your 7i, and you get a total of 7i. So, down below here, we're going to do a side note before we try this problem over here. If I said 3 plus 4i is equal to some unknown number plus 4i, well, if the i's are the same and these complex numbers are the same, that means your 3 would have to be the same as a. Or vice versa, if I had said 3 plus 4i is equal to 3 plus some unknown number times I, since they're equal and the 3's are the same, you would know what's in front of your i's would have to be the same. So your 4 would have to be the same as c. So down below here, if I have a complex number equal to a complex number, same type of thing. The real parts, the red, have to be equal. And the imaginary parts, what's in front of your eyes, have to be equal. Notice I said only what's in front of your eyes. So over here on the side, on our problem that we're concerned about, the parts that don't have eyes have to be equal. And then the parts in front of the eyes, not the eyes, only what's in front of the eyes would have to be equal. And so what's in front of the eyes has to be equal. And then what's underlined in purple, the real stuff without eyes, has to be equal. And then you can solve each one of these. On the left side here, we can just divide both sides by 2. On the one over here on the right, we can go ahead and add or subtract our 1 to both sides. And then we can go ahead and divide by 3. And we get this. So if you have a complex number equal to a complex number, the two real parts, the parts without eyes, are equal. And the imaginary parts, what's in front of the eyes, are equal. So here you have a complex number times complex number. It's 2 terms times 2 terms. So basically we get a FOIL like we would with normal algebra. You multiply together your first terms. Then you do your outer terms. And then you do your inner terms. And then you do your last terms. Remember 5i times a negative 2i. I times I gives you an I squared. So now we can combine together our like terms in the middle. And remember that I squared is negative 1. Oh, so that's really like adding 10 at the end. And 10 plus 2 is a 12 plus that single I. So side note over here on the right. Remember that I is the square root of negative 1. So what we have up here is really 3 plus a 2 square root of negative 1. And you should remember from earlier in the chapter that we don't like square roots in the bottom. And when we had 2 terms in the bottom where one had a root and one didn't, we always multiplied by the conjugate. That's what we're going to do here, is we're going to multiply by the conjugate at the bottom. Remember, conjugate is when you switch the sign in between. And if you multiply the bottom by that, you'd have to multiply the top by that. So on top, we can take our 5i and distribute it through 5i times 3, 5i times that negative 2. On the bottom, we have 2 terms times 2 terms, so we have to FOIL. First terms, outer terms, inner terms, and last terms. 2i times negative 2i, remember you get an I squared. So as we look here, this negative 6i and positive 6i in the bottom, they cancel. So on the bottom we have a 9, and then b minus 4, and then we have our I squared, which is negative 1. On the top we also have an I squared, so we could replace that with negative 1. So on the top we really get this. On the bottom we really get this. On the bottom we could add that together, get a 13. We can't add these together on top because they're not like terms. And you could leave it as one fraction like this, but technically speaking, it should be written as 2 separate fractions, a part that doesn't have eyes plus a part that does have eyes.